Today I'm going to present our work, which is called CASE. Stands for Comprehensive Application Security Enforcement. This is a joint work between my student and our collaborator from IBM Research. Again, my name is Long Lu. So before I get into the system, I just want to very briefly introduce the problem that we're solving, or the attack that we're trying to defend. So there's been a line of emerging attacks that we call module-level attack emerging from mobile applications. So what does that mean? If we look at today's mobile applications, unsurprisingly, we will see a lot of external modules being integrated into apps, and there are a great variety of them. Advertisement probably is the most common one, and then we have analytics, integration of various kinds of cloud services. And the granularity of those modules could range from libraries, typical libraries, all the way down to very small classes, external classes. So then you might wonder, what's the security problem here? Well, it turns out that these modules, sometimes they don't get along with each other. There's kind of conflicting interest going on between them. And here are some examples. Recently, there were reports on either malicious advertising libraries, which try to very stealthily collect user data, try to track user, or maybe even more aggressively collect very sensitive data from user. And secondly, there were several libraries that provides in-app payment services were caught to silently uploading users' contact data back to their server for various reasons. So again, these are just very not widely known. I mean, these are just reported cases that known in the field, and there are a lot more cases like this happening. So we generalize those type of attacks or threats using a term we call module-level attacks. And one thing I want to note here is that this type of attack could happen at two layers. For example, one module could target the other one, and at the same time, a malicious module could try to exploit or attack the underlying system. And it doesn't always have to be external module being the malicious attacker. It could be the other way. For example, the main app could be malicious and try to exploit or manipulate an included library. So enough background, you may be wondering, okay, why this attack is emerging and why it's getting more and more popular. So there are three major driving factors behind those attacks. The first one is that there's just increasing dependency on modules among apps. App developers tend to use a lot of modules to speed up the development, to increase the functionality of apps and so on. And secondly, there's actually a strong or increasing incentive for module developers to do things that they don't used to do, or to sort of peek into other modules to collect data, or to take advantage of other modules. And finally, this type of attack is quite easy to launch, and at the same time, it's very hard to prevent. Okay, so why it is hard to prevent, or why it is so easy to launch? To figure out that, or to answer that question, let's look at what are the conventional app security mechanisms could offer. So we know that it's quite common on major mobile operating systems. We have app-level sandbox, permission models of various sorts, and the problem here is that they mostly operate at application level. And what does that mean is that they treat individual applications as the minimum undivisible entity to enforce security policies. In other words, these line of defense or mechanisms do not directly apply to defending against module-level attacks. And also, another line of work, mostly coming from academic research, there's a rich body of work that tries to improve on, for example, sandbox or permission models by introducing very fine-grained sub-objects. For example, in addition to, say, one app could access the internet, how could we finer grain this permission and even introduce context into this permission enforcement? But again, the problem there is that most of these works still treats individual apps as the minimum security entities. So we, in fact, identified 3 core requirements that have to be met for defending against module-level attacks. First of all, a capable solution needs to support fine-grained modules. It cannot be as coarse as a library. It could, the granularity needs to be variable. And secondly, the system needs to provide complete mediation among module-level activities. It's a completeness guarantee. And thirdly, the system needs to be robust, meaning it cannot be easily bypassed or even tampered with by attackers. So now let me introduce CASE. CASE is a system with the goal of enabling comprehensive security enforcement at the app module level. Module could be broadly defined and could be of various sizes, and which I will cover shortly. We took an approach that we call it very practical approach. Basically, we use offline rewriting of applications plus runtime monitoring to enforce policy or to enabling policy enforcement without changing the operating system or without changing the middleware of the operating system for obvious reasons, because this approach could lead to very easy and wide deployment in the wild. And the system purely operates in user space. So here are some example use cases for CASE. How could they be used to defend and stop user-level attacks? First, as I mentioned earlier, there were malicious advertisement libraries found to steal user data. And here, if we can enforce policies at module level, we can say, for example, only allow ad libraries to contact back to its own server and does not allow ad libraries to directly access, say, GPS sensors or user contact data and so on. Similarly, we can use this for in-app payment libraries or other examples. So before I go into the details of the system, I just want to highlight the threat model here. What do we trust here? Well, let me start with what do we not trust here. We assume that any modules inside app could be malicious, outright malicious. They would try their best to either tamper with the system or try to bypass the system. On the other hand, we need to trust the OS, meaning the OS has not been compromised beforehand, which is a very realistic assumption, because given that we're dealing with, or we're trying to prevent module-level attacks, if the OS has already been compromised, then there's not really much point of doing or launching this type of attack. So what's challenging about realizing this idea? So first of all, as I said, we need to meet the completeness guarantee. Given that we adopt a relatively strong or adversarial threat model, we need to make the system robust against possible attacks. And secondly, we need to avoid any efforts or avoid any possibility for malicious code to bypass the system. So for the rest of the talk, given the limited time, I'm going to focus on 3 core techniques that we came up to achieve completeness and robustness. And I'm going to refer you to our paper for the rest of the system design or the policy language and policy enforcement mechanisms. So these 3 core techniques are dual-layer interception. It is an interception mechanism that we came up to first enable the recognition of very fine-grained modules and to completely monitor and intercept the interaction between those modules. And second technique is what we call native safe pages, and this is a technique how prevent malicious native code from manipulating or tampering with our system. And third technique is called conceal handler. I'm going to go into each one of these and explain to you what do they do. Dual-layer interception. So what are the 2 layers here? They are the VM, language VM layer, and the system call layer. So if you look at this slightly complicated graph here, if we imagine two modules inside an app try to communicate with each other or even communicate with the underlying system, there are two inevitable interfaces this module has to cross. One is the interface inside the language VM. Here, again, we use Dalvik or Android as the prototype platform. So, for example, for class A to talk to class B, it needs the help of the VM to dispatch the invocation or to facilitate this communication. And similarly, if class A needs to eventually make a system call, say access file system, it not only needs to go through the VM, but also the system call interface. And also I want to highlight that our system does consider native code embedded inside apps, and they could be completely malicious as well. So this dual layer interception does enforce or does enable a complete interception. And in terms of the technique that we use to realize those interceptions, there are kind of typical techniques. These are not really the true contribution of this technique. And the true contribution here is that we identify or we derive the set of function interception points that if we can completely intercept them, then all the interactions between modules and systems will be completely handled and mediated. So this set spans 3 executables or 3 libraries. They're libc, which is the runtime library, Bionic library, and the linker and the virtual machine itself. If it is a Dalvik, it's libdvm. If it's the latest art, it's libart. There are 30 native functions contained in the set, and there's, I'm not going to go through all of them, but these are the different purposes for intercepting these functions. They include class management, reflection, and even native level process and memory management. Here's a snapshot from the paper. The second technique, as I said, is designed to prevent malicious native code from bypassing this dual-layer interception. So what do they do? If we think about how an attacker could go about attacking the system, the most direct and most effective way is actually directly manipulating the data and the code in memory, because we allowed native code in this case. For example, for a malicious module to collect data from the other module, instead of going through the regular Java interface or even reflection interface, it can directly go to the internal VM data and try to extract meaningful data and structure from there. So we propose this native safe page to facilitate the protection. And there are 2 types of native pages. One for protecting system interface, as I show here, and the other one is for protecting the internal VM data. And they're based on the idea of paging-based logs. But what we do here, and one kind of smart trick we adopted here, is that we do not incur per operation lock and unlock, so that the performance could be good, and at the same time we maintain the security. So this third core technique is called concealed handler, and this is a generic technique that you can think of as a way to allow function invocation without the caller knowing the address of the function. So it leverages the standard POSIX signals and basically converting function invocation into signal handling. So in this case, the caller doesn't need to know the address, and the OS will be able to stealthily forward the invocation to a concealed handler, and it serves as a master dispatcher routine. Okay, now let's look at the evaluation results. We used 3 sets of apps to evaluate the system. The first set contains roughly 420 popular apps. They were selected from those from each category from the Android App Store, and the second set contains 20 apps that were randomly selected from S1 for in-depth and manual analysis. And the third set is the Android default unit test for Dalvik or ART virtual machine. So the results we got, first of all, for the cost of rewriting apps and the compatibility test, each app took about slightly more than 6 seconds to be rewritten, and the size of the executable increased about 4%, and there were 0 apps failed to be rewritten or failed to start. And during runtime, the overhead for starting the app increased about 0.1 second, and this is mostly because of the initialization that is needed at the beginning to set up the dual layer interception. And the overhead, the power consumption overhead, which we tested in a battery exhaustion manner, show that the battery overhead increased about 6%. We also conducted per task end-to-end overhead test, and the overhead we measured was for the per operation overhead. It was almost 4%, and the end-to-end, meaning from the starting point of the app till the end, the overhead was about 5%. Okay, so now let me conclude my talk. So we propose CASE, which is a system that tries to enable fine-grained module-level security enforcement. Again, due to the limited time, I didn't really go into the policy part. I only introduced to you these core techniques that we use to enable interception and to achieve robustness. And secondly, the approach does not require any operating system level changes or middleware changes, so it's practical for wide adoption and can be instantly used to protect these emerging attacks. And third, the design is shown to be robust against both malicious Java code and native code. This is actually one of the key contributions of this work, that is to use these typical interception techniques, but to make them very robust in an unusual threat model, or a very powerful threat model. And lastly, we evaluated the system against a large number of apps, and the results show that the overhead is acceptable, well, at least by our standard, and we hope that the system could be used or deployed in practice. So, with that, I'm happy to take questions, and thank you.